We're going to open up our new unit of ions and what's called periodicity by looking back at electron configuration for just a moment. Make sure you have your spiral open so that you're ready to write everything that I do. You're also going to be not decorating, but writing on your periodic table today. The reason that we're going to revisit electron configuration is that valence electrons are going to be absolutely essential for this whole unit. With that in mind, I need you to be able to count valence electrons much faster than I've previously shown you to do. Let me show you what I mean. So there's the periodic table. All right, I've seriously abbreviated that lower area where the D level lives for electron configuration. There's a cheat, a shortcut you can use to look at an element and figure out how many valence electrons it has without going 1s2, 2s2, 2p6, 2's the biggest energy level. Let's count how many arrows there are there. If you go through that process with the new stuff, it's going to take you forever to get to an answer on what we're going to start doing now. So here's what I want you to do. Look at your periodic table, and I want you to verify that you can find the numbers that I'm writing. Do you see those values that I just wrote on your periodic table? All right? They're the columns. They're the numbered columns. Now, down here is 3 through 12. This cheat that I'm about to show you to count valence electrons doesn't work for these guys down here. They're called the transition metals, and they're funky, so we're not worried about them right now. These numbers up here tell you the number of valence electrons all the elements in the column have. Now, it's not quite that simple. It is for 1 and 2. But what's the maximum number of valence electrons an element can have? You can't go over 8. So we can't say that these have 13. That's impossible. Instead, the way the cheat works is all the elements here have 1 valence electron. All the elements there have 2 valence electrons. All the elements here have 3 valence electrons, 4, 5, 6, 7, 8. It counts 1 through 8 just by using this little number cheat. Now, for those of y'all that need a visual way to get these guys, just cover up the 1. All the elements in column 13 have 3 valence electrons, 4, 5, and all the way up to 8. Now, you can verify this with electron configuration. I'm not showing you anything new. I'm telling you that if you take aluminum, who lives right here, and you draw out his electron configuration and you try to figure out valence electrons, the electrons that are just in the highest energy level, based off his location, how many do you think there will be? There's 3. Aluminum has 3 valence electrons. So you could have answered a few questions on that last test a little quicker if I had showed you this, but I needed you to be doing the configurations at that time. So, let's practice a little bit. I need a periodic table. No answering out loud, but write it down in your notes. I'm just going to give you an element, and right next to it, you're going to write how many valence electrons there are. It's good to have in your notes just so your eyes can see examples. So, don't answer out loud. Magnesium. How many valence electrons does magnesium have? In your notes, put Mg. What's the answer? Magnesium has 2 valence electrons. He's in group column 2. Iodine. How many valence electrons does iodine have? Hey, quit answering out loud. You're too smart for your own good. Grab a cheat sheet. Right behind me. How many? 7. Does everybody see how iodine has 7? Because he lives right here in group 17. Why not make our thing pretty? All right. Magnesium. Iodine's down here. All right. All of the elements in column 17 have 7 valence electrons. Argon. How many valence electrons does argon have? 8. He's got a whole octet. All right, remember those noble gases over here? You already learned where the noble gases are. They're the only 6 elements that already have a full octet because they have 8 valence electrons. Do you see how I'm doing this? If you look at your cheat sheet, the very first statement says, the octet rule states that all elements crave 8 valence electrons. Atoms will gain or lose valence electrons in order to achieve an octet and become stable. This is ionization. Look here. The elements are going to move their electrons around. We're taking our first step towards bonding, which will be the unit after this one. But iodine here is going to do stuff with his electrons to make him get to 8. And that's what we're going to look at now. Find magnesium again. All right, magnesium's living right here. How many electrons does magnesium have based off his periodic location? Yeah, he's got 12 total electrons. All right, because his atomic number is 12. How many of those are valence? Just 2, right? Because he's in that second column. So he's got 12 electrons, 2 valence electrons. What does his Lewis structure look like? How many dots? Yeah, 2. Remember the way the Lewis dot structures work is it's a dot for every valence electron. So using this cheat gets us to the valence electrons in the Lewis dot structure very easily. Let's do it for that whole row that magnesium's in. Watch what I'm going to do. I'm going to draw out every element in the row. I want you to do it too. Draw this picture in your notes the exact way that I have. Those are all of the elements in the third row. Now, before I show you some trends here that we've got, I want to talk about what the word ion means. To be an ion, you have a charge. We haven't had a charge yet, being a plus or a minus. So, if I have that element right there, magnesium, just written like that, he's not an ion because he doesn't have a charge. But watch, 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 watch. Now he's an ion. If you have a plus or a minus associated with you, you're referred to as an ion. Ion, not an ion. Let's do another one. Is that an ion or not an ion? Not an ion, it's just oxygen. Now, is it an ion or not an ion? It is an ion. Hey, look, I can take this one beautiful step further. You see that negative symbol right there? A negative ion is referred to as an anion. All right, and this is right. This is at the top section of your cheat sheet. So not only is oxygen an ion in this case, we call him an anion just because he's got a negative charge to him. This is all vocab. Is that an ion or not an ion? Why is it not an ion? It's got no charge. Watch, 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 watch. Now is he an ion or not an ion? Now he's an ion. You see that positive charge right there? This is another vocab word. We call him somebody say this. A cation, not a cation. Don't call him a cation. That's weird. Yeah, a cation. For some vocab help, because you definitely need to know that having any charge makes you an ion. But to take it a step further, a negative charge is an anion, a positive charge is a cation. But for vocabulary purposes, look at the word cation. There's actually a plus symbol in the middle of it. Do you see that? Do you see the plus symbol in the middle of the word cation? All right, so it tells on itself. There it is. What's that? Don't say sulfur. Not an ion. Not an ion. Watch this. Watch this. What is he now? An anion, because he's negatively charged. I'm going to show you where these negatives and positives come from in a second. I just want you to have the vocab down first. What's that? Not an ion. No plus, no minus. Watch, watch, watch. What is he now? A cation, because he's got a plus there. This should be very simple. I cannot keep track of this. Let's go back to the picture that you should have drawn in your notes. We already did magnesium's Lewis structure because he's in the second column. How many dots does sodium have? Just one. He's got one valence electron because he's in the first column, right? How many dots does aluminum have? He's in group 13, column 13, so that's 3. So I want you rather, finish drawing the Lewis dot structures real quick. This should be very simple. Call me over if you're not sure where it's the dots. But draw the Lewis dot structures for the rest of those. Yeah. And I'll draw them too. Any questions about the way I've drawn my Lewis structures? Ask that. We're at the very beginning of stuff, guys. Don't start off confused. We're good? During ionization, these elements are going to get an octet. They're going to become stable. And here's the way it works. They either want, what's the magical number for the octet? 8. They either want to get to 8, or here's the other one. Look here, look here. They either want to get to 8 or get to 0. 0 is just as good as 8 valence electrons because, for example, if sodium gets rid of that dot, he actually drops backwards to the last noble gas status, which is just as good in terms of stability. So listen to that again because it's a really big deal because a lot of students don't get what we're about to do in a moment. There's 2 magical numbers to become stable. 8 is the real number. But from a visual standpoint, 0 is just as good. Let's take a look at sodium. If I say that sodium wants to become happy and stable and have an octet, how many dots does he need to gain to get to 8? He would need 7 more dots. Everybody see that? He's got 1 because he's there. He would need 7 more. How many dots would he need to lose to get down to 0? Only 1. I would just have to erase that dot. He'd have no dots, right? Which do you think is easier? Is it easier to lose 1 of something or go and find 7 of something? The smaller number will always win. I'm about to ask that question a lot. Whenever I give you that choice, the smaller number is always going to be easier. It's easier to get rid of 1 thing than it is to find 7. Now, here's where I'm going to break your mind in half. So listen. If sodium has protons and electrons, he's got more than that. And what did we just say we're going to do? We're going to, no, lose one. All right, because one was the smaller. Watch what happens if I lose one. There it is. He just lost one. Keep watching. He lost one. Remember, every time you have a plus and a minus, they cancel out. Remember that? Watch what happens. What are we left with? A plus. If sodium loses an electron, he becomes positive 1. The reason this really messes with your mind is because he lost something and became positive because of it. And that's totally reversed of the way that your brain's wired. You think that if you lose something, you should become negative. The problem is that we're losing negatives. They cancel out. Let's do another one so you can see what just happened. Why can I not keep track of the eraser? Let's look at magnesium. All right, let's take a look at magnesium. Look at his Lewis structure. He's got 2 dots. How many dots does magnesium need to gain to get to 8? I'd have to draw 6 more. How many dots does he need to get rid of to get down to 0? He would just need to get rid of 2, right? He's got 2. He either needs to gain 6 or lose 2. What's he going to do? Always pick the smaller number, all right? Magnesium, again, I'm just going to draw. Remember, they all start off neutral. So the same number of pluses and minuses. We said that magnesium's going to do what? Lose 2 electrons. Watch. There's 1 electron gone. There's 2 electrons gone. Now let's see what his resulting charge is. Every time you have a plus and minus, they cancel out. Ooh, what's he left with? I want you to be writing this the exact way I am. Magnesium wants to lose 2 electrons. If you lose electrons, you become positive. We can even take it a step further. Magnesium wants to be a, put in a vocab word. Magnesium wants to be a cation. He wants to be a cation, right? Look at that. Remember the plus, a cation? Start to connect some of these dots. Let's skip over to phosphorus. Let's take a look at phosphorus. All right? Phosphorus, focus. He's got 5 dots around him. How many dots would he need to gain to get to 8? He would need 3 more. How many dots would he need to lose to get to 0? What's he going to do? Lose 5 or gain 3? The lower number's 3 this time. And we said gain. So watch this. I'm just going to draw. It doesn't matter how many pluses and minuses I draw here. All right, as long as there's the same amount. Aluminum's really got 13, right? I think so. Now, we said he's going to do what? He's going to gain, phosphorus. We're doing phosphorus. He's going to gain 3. Watch. 1, 2, 3. Electrons are negative. He gained 3 electrons. Let's take a look. What's his resulting charge? Phosphorus gained electrons. When you gain negative particles, you become more negative. Yes, ma'am. These dots? It doesn't. That's what I'm saying. It doesn't matter. If I started with just 1 of each and then I gained 3 electrons, you would have ended up with the same answer. So it doesn't. This step isn't a part of your problem solving. I'm just trying to give you a visual. Really, but here, let me answer her question. She said, how many pluses and minuses do you draw? We just did phosphorus. Phosphorus has 15 protons, right? Look at phosphorus. Verify. Phosphorus has 15 protons, right? Because he's element number 15. So phosphorus really has 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right? Hey, remember, the number of protons is always equal to the number of electrons, right? Remember that? Remember? They're the same number? Yeah? 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 Say yeah. Good. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's the right one. If I was showing phosphorus, that's it. But watch how I get the same answer. Phosphorus wants to gain 3 electrons. There they are. And then all that disappears. And he's got -3. So I was slowing down the process, but that's what's really happening. Good question. I'm gonna do that in every class now. I got to yell. Let's do chlorine. Chlorine has 7 valence electrons, therefore 7 dots. How many dots does he need to gain to get to 8? Just 1. He's 1 electron short. How many does he need to lose to get down to 0? He'd have to lose 7. What's he going to do? He's going to gain 1. So let's draw just the same amount. All right? We said he's going to gain 1. What's his resulting charge? -1. Hey, what would we call chlorine? We'd call him an anion because he's negative. Hey, here's what I want you to do real quick. And if you see a pattern, then you don't have to go through all the steps. But I'm going to ignore that row, that column, because he's funky. But there's 3 spots there. Find the charges, just like I just did. I need a plus or a minus with a number there, a plus or a minus with a number there, and column 18 is fine. Fill them in. For aluminum, you should have said aluminum can either lose 3 dots or gain 5. All right, it's easier to lose 3. Whenever you lose electrons, you become positive. All right? And by the way, that sentence there is the golden sentence because that's the sentence that so many of you will never understand. If you lose electrons, you become positive. But the good news is if you look at the definition of cation, it says cation is an atom with a positive charge. Electrons have been lost. It says it right there on the sheet. So while you're sitting there thinking this is weird and hard, it's here. It's here. All right? Sulfur can either lose 6 or gain 2. Lose 6 or gain 2. 2 is the smaller number. We're going to gain electrons. By definition, gaining electrons creates anions. What did you say for group 18? So what do you want to do? What'd y'all put up there? Nothing. You should have put nothing. The noble gases won't let you do anything to their electrons. They already have an octet, meaning they're completely stable and won't react. For this to happen, this stuff we're talking about, for sulfur to gain 2 electrons, he's got to go get them from somebody. All right. Again, I used this example once. When you saw a gummy bear go psycho on the first day of school, it's because when the gummy bear and the liquid mixed together, they recognized that both of them looked like this and not these elements. But both of them were in this situation where neither of them had 8 or 0. So they started taking electrons from each other, and we saw it as crazy light and smoke. All right? It's these reactions that will happen that will make these other elements eventually stable like the noble gases. You see these numbers up here? +1, +2, +3, -3, -2, -1. They are your life through February. So, on your periodic table now, I want you to write them there. On your PT, bold and beautiful, because I'm telling you, you're going to use them all the time. +1, +2, +3, -3, -2, -1. Those 6 values. You shouldn't have anything above the bottom area. You shouldn't have anything above group 14. You shouldn't have anything above group 18. The reason that these charges are written above the column instead of just like bisulfur is because the charges apply to the entire column. In other words, if you look, what element's below sulfur? Selenium, all right? How many dots does selenium have around him? How many valence electrons does selenium have? Say, look, selenium is in the group 16. If I cover up the 1, it tells me he's got 6 valence electrons. My point is that all of the elements in the column have the exact same Lewis structure. Therefore, they're all going to do the same thing. Selenium can either lose 6 or gain 2. He's going to gain 2. When you gain 2 electrons, you become -2. So the entire column is the same. There was a question on your test that a lot of you struggled on, that it gave you this. It gave you an element that doesn't exist. And it said that element could be what? And what other element would also look like it? Do you remember that question? All right. So now that you know what you know, all you would have had to do is say, well, there's 7 valence electrons, so it had to be an element in that column. And the element that's going to be like it should have been another element in that column, because all of the elements in group 17 have the exact same Lewis structure. I think the answer was iodine and chlorine, but anyways, that's fun. Any questions before we go into our last topic of the day? If you look at the very bottom of the front of your cheat sheet, you'll see a section called Naming Ions. This is a very 4th grade skill, so that's good news, but you need to learn how to do it. That's lithium. What is lithium's predicted charge? Find lithium, run your finger to the very top of the table where you just wrote something. What is lithium's predicted charge? +1. Everybody see how lithium has a predicted charge of +1. See a cation or an anion? A cation. Cations are positive. What I want to show you how to do is how to say him, how to verbally talk about lithium in his ion state when we're having a conversation. If it's a cation, the rule says that you're going to say the name of the element. What's that element? You're writing lithium. And then, in a separate word, you're going to say the word ion. This is called the lithium ion. Now, that sounds really stupid, and I can't even believe you're telling me this. Duh. But the anions are a little different. If it's a positive, though, you just say the name of the element and then separately say the word ion. Find calcium. Find calcium. What is calcium's predicted charge? +2. Everybody see it? No reason to guess. Everybody see it? Find calcium. Go to the top. Do you have a +2 written above calcium? Yeah, yeah, yeah. How do I say calcium? A calcium ion. Calcium because that's his name. Ion as a separate word because he's a cation. Let's look at the other thing. Find nitrogen. Find nitrogen. What is nitrogen's predicted charge? -3. Written like that. Nitrogen wants to be -3 because he's stable if he is. All right? He lives right there. When it's an anion, something different happens. Instead of saying nitrogen, I'm going to change the ending of the word to ide, I-D-E. This will take some getting used to on putting the ide in the right place. But how do you think you say the word nitrogen ending in ide? Nitride. This is nitride. You can say nitride ion. It's right both ways. Just nitride is good, or the nitride ion is fine. But the only reason that I added the "ide" is because there's a negative symbol there. You don't do it when it's a cation, only when it's an anion. Let's do phosphorus, because I like to watch you try. Phosphorus has a predicted charge of -3 because he wants to gain 3 electrons to get to 8. How do you say phosphorus when he looks like this? Oh, good. I'm glad somebody did it. Yeah, it's just phosphide, not phosphoride. But if you put phosphoride, or even if you put phosphoricide, you keep the whole word and add "ide" to the end of it, I'm totally giving you credit. All right, I can see that you knew you were supposed to do something like that, but you're just clueless on where to do it. All right, you're not a chemist in here, I get that. But it's phosphide. Or you can say phosphide ion, whatever. Do you see how I'm doing this? So let me give you a couple to do. I want you to do aluminum and iodine. Just name them. How would you write the names aluminum and iodine? Here's my thought process. I hope yours was the same. Aluminum is in group 13, which has a predicted charge of +3. That is a cation because it's positive, which means I'm going to just name the element aluminum and then say the word ion afterwards. There's no such thing as an aluminide or an aluminide ion. It's always very wrong. So don't add "ide" to cations. Iodine's one of the fun ones because even when you get it right, it looks wrong. Iodine is in group 17. He lives way down here below chlorine, which means just like chlorine, he has a predicted charge of -1. He's an anion, which says I need to not say iodine. I need to say iodide. An iodide ion or not. You don't have to put that ion, but you can. Questions over ions? Y'all have a great day.